All right, great, great. All right, wonderful, Alvin. Wonderful, Alvin. So you have been able to use Excel, and I would actually recommend that you try Tableau as well. Okay, because Tableau is a great idea because in these days, most of the analytics is being done over Tableau. Yes, Sunny, I saw that. It's a good work you have done. And all right. So, hello everyone. Okay, hello to the wonderful class. And so let's start the session. Okay. All right. All right. So, okay. So there are 15 people in the session. All right. So far we have discussed about how does Spark work? What was Scala? So we learned about Spark, then we learned about Scala, then how to get started with Spark, the general concept about Spark like RDD and how does driver and other machines communicate and how does the magic happen. Okay, then we learned about transformations and actions. Okay, the various kinds of transformations we have learned: map, filter, flat map, and then we also learned about key value kind of data types in the RDD, where we could do various kinds of operations based on key. Specifically, the data type uh, where specifically where we were trying to join two RDDs using a key. All right. So there are a lot of operations available on an RDD, and I forgot to tell you that you can just press tab and it will show you all possible functions on an RDD. Okay, so and then you can look it up. So most of the functions, because they keep on adding these new functions every now and then. Okay, so for example, we are now in Spark. So in Scala shell, this is Scala shell which is connected to Spark gives us an object called SC. Okay, and this object, if you press SC dot and then press tab twice, it gives you the list of all the functions. All right, so these are the various functions. Out of this, we have only dealt with one, the text file. Do you see text file anywhere? All right, so also we have dealt with parallelize. All right, and was there anything else? Yeah, we will talk about few more of these and you will get the entire picture. All right, so let's say you want to read data from Tachyon file system. You can use this, and there were I mean actually you can read using text file itself by specifying a different URL. Similarly, you can read the data from Hadoop using this newer API. Older can be accessed using this. Okay, so there are quite a few functions here. There are quite a few functions. So all you have to do is whatever object you create. Okay, like for example, we have created this RDD called X, right, by parallelizing. So if you just type X and press enter, it says that it's a parallel collection. Okay, nothing so special about it. So you can see when you say X dot, then all the possible functions are available to us. Okay, like persist saves the data, caches the data, then save as text file saves the data to the disk, and sample we have talked about, take we have talked about, take sample we have talked about, and we also talked about map. We also talked about um, see the for each. We also talked about fold, flat map, then filter. So so basically you can look it up in the API of Spark. So you can simply go to the documentation, and there in the API almost every function is listed. All right. Most of the functions are on the same line as what we have discussed so far. The common thought process amongst all the function is, how do we convert a processing from local into distributed? All the things that you wanted to do local that you can still do here, because it's a scalar prompt. If anything you want to do with Spark, we start with SC, which further gives us the RDDs. You can create RDDs, and then on top of RDDs you can create further RDDs, and then you can start the processing by calling an action. Okay, so there's a common philosophy amongst most of this computation. All right, before we start, do we have any question? So we have gone through most of it. All right, so here is one exercise. Did you try this exercise? Okay, in this folder you have to find most oftenly most often 10 IP addresses. Okay, if you want, I can just copy this code for you so that you can right away start trying out as soon as the session ends. And so I've just written a small example. You might do it more efficiently than I did. Okay. Okay. So basic idea here is that we access the logs, and then just test whether we have been able to load this folder. And then before that, before you start, you just take a look at this folder, what is there inside this folder. And then here you can check, you can filter all the records by creating a filter function which checks whether the line contains this kind of expression. Once only the lines containing the IP address is left after this, then we extract the IP address. And how do we extract the IP address? By doing the map. Okay, so we are saying line and extract IP address. So basically we are handing over this extract IP address to the RDD, and it'll run this function. It'll run this function for every line because we are calling it under map. Okay, so we are saying whatever is the line that you basically capture this particular part of the pattern, and this pattern starting from bracket to bracket will give you the IP address, and we return that part. Okay, you can test this once you have written this function. You can test it out. You can test it out on local data. Okay, without using Spark. Okay, all it does is it takes your function and runs it on every line. And once that's done, there'll be a new RDD called IPS. This RDD will contain the each record would be an IP address. Okay, and once that's done, we just say reduce by key, and also note that it'll be IP address, comma 1. Okay, so those tuples can be grouped by reduce by key, and that's it. All right, once that's done, then we can sort the data and take sort the data by second argument. Second is the number of times each IP address is existing, and then we do this. Also, we could, after reduce by key itself, we could say take ordered, and then order, basically combine these two together. All right. So feel free to experiment by experimenting, because sorting and take order take can be combined together. All right. So sometimes it's useful to partition data, not helpful if you need to scan the data on dataset only once. It's equivalent of indexing the database. Okay, those of you who have indexed the database would be able to connect with it, that if you just need a table only once, like a temporary table, then you don't really need to create an index. Okay, and so similarly here, if you needed RDD multiple times, you can do the partitioning accordingly. Okay, so it causes the system to group the elements based on the key. Spark does not give you explicit control which worker node has which key. Okay, so it does not give us a great control over which worker node is going to have which key, because that's something partitioning logic decides based on how many keys are there and so on. It lets program control / ensure which set of keys will appear together based on some hash value. For example, for example, it could be based on some hash value, or you could also do range sort. Okay, so basically it lets the program decide which bucket one particular key goes to. You remember our partitioning logic in case of MapReduce? Given a key, that partitioning logic will say that put it in first bucket, second bucket, or third bucket, and so on. Similarly here, we partition the data. Let's take a case of a very interesting scenario. Okay, let's say there is a table called user data. User data contains the information about every user's subscription of topics. That I'm interested in politics, you are interested in technology, and so on. So user data keeps those list of topics. Okay, and it keeps on periodically combining user data with last 5 minutes of events. Okay, an event is the actual behavior. One is that I have subscribed to certain topics, and second is my actual behavior. My actual behavior could be that I like Hollywood news, but I don't want to subscribe, I have not subscribed here. So that is captured as part of events here. In this example, there are two tables. Okay, one is events, other is user data. Okay, now your objective here is to find out how many users visited a link that was not one of their subscribed topics. Okay, how many users visited a link that was not one of their subscribed topics. All right, so imagine that user data is loaded from this place, and then here we are loading events from another file. Using sequence file means if the data is saved in the sequence file format, instead of using text file, you can use sequence file. Now, we are loading the recent events, and then we are joining it with the user data. Okay, user data. And then we are doing filter. Okay, we are doing filter, and this is our function. This function, forget the lambda for now because this is in, okay, we forgot to remove lambda. So this is basically checking here that all the topics that are not part of a particular, after joining this, we are trying to figure out what are the topics a person was. So when you join these, you will have user ID, then the recent topics that have been there, as well as the subscribe topics, recent topics, subscribe topics, and the user ID. Okay, so you have to just check, run a filter, and check if user info dot topics contains link info dot topics, meaning is the user's topic is in the recent activity. All right, and that's all. And then you do the count. So every time you do the count, this joining will happen, filtering will happen, and this number will be calculated. Okay, so that's what happens here. As soon as you execute this function, it's going to load this data, join it with this table, and then filter it. So and then and this whole thing happened from here till here. Everything would happen as soon as you call count. Now, you can see clearly that every time this function is called, events get loaded, right? Similarly, join, and again, the same thing is happening. And you can see that this table, user data basically is not really cached, right? User data is not really cached. Sorry, it is cached here. I'm sorry, it is cached. So user data has been cached so that joining becomes easier. So every time we join it, we don't read this part of data, and that's it. But here, since joining is happening based on the key, right? So we can take some advantage. So every time joining happens, this kind of transfer happens, right? When you are joining things, there'll be a shuffling. Okay, just like in the reduce phase of MapReduce. Okay, so there'll be some keys will be here, some keys will be here. So this kind of phenomena will keep on happening. So user data is getting joined with events, and this is what we are getting. Okay, so you can see that there's a lot of network communication. So if we order one of the data sets by using partition by, so if you say partition by, the key value, the data will be partitioned based on the key, okay, based on the key. And therefore, while joining can take advantages of partitioning, okay, so that only events from various the events need to be ordered before joining, while the user data is already kind of ordered. So there'll be less of network transfer or shuffling. Okay, you can partition data. You can partition data by loading this way, and then say partition. All right. So I'm trying to give you a good example here. So we loaded this as LR. Okay, LR is your RDD. It's 1,000 numbers, and their RDD we have created by parallelize. What does zip do? Zip basically kind of zips this and this together, so that first element of this one and first element of this one and first element of this one basically are combined as key and value. Okay, I'll show you quickly. So, okay, so you can see that if I say LR1 dot take 10, so you can see that 1 1 2 2 3 3 and so on, because LR contains 1 2 3 4 5. So so we are saying zip this with itself, which is equivalent of kind of putting them this way, and then creating tuples by zipping them together like this. You see, like this. Remember, like if there was a zipper in between, these will join. Remember, when you're zipping something in a physical world, there are two sides of the zip, and they start combining together, right? So that's what we call zipping. Okay, so zipping basically generate the key value pair from two two RDDs. Also note that zipping will throw error if the two RDDs are not equal in length. Okay. So this is how you can, once you have zipped data or you prepared a key value RDD, you can simply repartition, and repartitioning automatically picks up the key and generate the hash code and does the repartitioning. All right. So this is one form of optimization. Okay. So RDD's partitioner, you can find out who is the partitioner using dot partitioner. There are many. Wherever there is a shuffling, just like join operation, there is a group by, co-group, reduce by, and so on. Left join, right join, and all of these, including lookup, all of these functions kind of just the way where clause takes the advantage of indexing. Similarly, all these functions take the advantage of partitioning. Okay. Here the network transfer is very important. Yes, those functions don't do the partitioning automate. There's a default partitioning, but that's not based on the key. Okay, there's default partitioning, but that's not based on the key. It's based on certain criteria. Although while we are joining two data sets, a lot of shuffling is happening, but that shuffling is not retained. That shuffling is not retained after, let's say, join operation is over. So you might want to partition your data before joining. This partitioning, as I said, is great if your data is going to be used again and again. In those cases, persisting and partitioning helps. It's like saying caching and indexing helps if you need certain data again and again. All right. Very good question, Jiankun. All right. So here we are saying that partition by, and then we are passing our own function. In the same way, in Scala, you can pass your own function to convert certain data into a number. Okay. So this is how you can do that. All right. Okay. So here is one example problem called PageRank. How many of you have heard about PageRank? Nobody? Sunny has heard. Okay. Nitesh, Srini, Hang. All right. Okay. So PageRank is algorithm that's what started Google, but recently Google is saying that they don't use PageRank anymore. A question from Jankun: can you partition by multiple fields? Yes, you can write a function which can which takes a record and can custom partition. The way here we are saying that we are partitioning URL based on the net location. All right. Yes. So PageRank was one of the algorithms which got Google started. And the main aim was to assign a measure of importance to each document as in each website. Okay. And based on how many people or how many websites are referring to a particular website, based on that, it gives an importance. Also, it's also if the websites which are pointing to a particular website, if those websites are very important, then the website which is being referred to becomes further more important. Okay, so if I'm being referred by the people who holds a lot of better rank than me, then my rank improves, and then and the chain reaction keeps on going. Now you can see that this algorithm has to be iterative. We start somewhere, we keep on computing rank again and again, and everybody's rank will keep on changing, right? because my rank will get evaluated because of that somebody who I'm voting, their rank will improve and so on. So this algorithm is better implemented as iterative. Okay, so this kind of algorithm are better done with GraphX, because that's the reason why GraphX was created, a library to operate on graph. Okay, the algorithm is very simple. You initialize each page rank to 1, and on each iteration, every page P send the contribution of this much to its neighbors. Okay, and then the process keeps on going. So each page rank is 0.15 plus 0.85 into contributions received. And how much contribution can a page give? My rank divided by who all I am voting. Okay, so if I'm voting, if I'm referring or voting somebody, okay, and I'm giving vote to 5 people, so whatever is my rank gets divided by 5. That's my contribution to their ranks. And if you're receiving, then the way your page rank will be computed, 0.15 plus 0.85 into total contributions received. All right, if you received only one contribution, your page rank will remain 1. And you keep on repeating second and third step again and again until the overall rank converges. Okay, so is this clear, or should I give a small demonstration? It's interesting algorithm. Let me just define it. You will just notice that even if there is, even if there are three, four nodes, okay? Even if there are 3, 4 nodes, the problem could become very complex very soon. Okay, so let's say there is CloudX Lab, there is no big data, and there is Spark, and there is Hadoop. Okay, and then there is, let's say, give me some ideas. Let's say, one of the people who are using our labs is say Simplilearn and say Manipal. Okay, all right. So Simplilearn is voting to CXL because they have mentioned a link on their website. Similarly, Manipal is also voting to CXL. Similarly, KBD is voting to CXL, and CXL is linking to Hadoop. Or let me just put Spark to avoid too much of, yeah. All right, so you can see that KBD also votes to CXL. Simplon also links to CXL. CXL is CloudX Lab, by the way. Okay, that's our lab, and many people are using it, so they are linking to this website. Okay, the example is clear. Now, who is most important out of all of these? Quickly. Yes, correct. Why Spark is most important? More links. Now, question is, what if Manipal also votes to KBD? No change. Now, who is the lowest out of all? Manipal or Simplilan? No, based on this algorithm, you saw that a rank basically, yes. Yes, so actually Simplilan and Manipal will both be equal. All right. So as per this graph, now let me just tell you this way. Okay, So initially, everybody gets 1.0. Is it visible to you? Okay, let me just, I think I can type better than writing. Okay, so initially, everybody gets 1.0. Okay, all right. Happy? Now, initially we give everybody equal rank. Now we start from one corner and then reevaluate their value. And the way we reevaluate their value is, reevaluate their value. The rank becomes 0.15 plus 0.85 into contributions received. How much did Simplilearn receive contribution from anybody? 0, right? So it'll be 0 contribution. 0 into 0.85 is 0, which means it'll become 0.15. Good? Similarly, Manipal also will become 0.15. Okay, so we are re-evaluating the rank. We gave them all equal rank earlier. All right. So you can see it's an iterative rank. Now for KBD, KBD is being ranked by Manipal. Manipal, right? So Manipal is having 0.15 value. Okay, Manipal is having 0.15 value, and it's referring to two people, CloudX Lab and KBD. All right. So KBD would get how much? So 0.5 divided by 2 went to this. Okay, this went to 0.075. Okay, and similarly, this also got this. Okay, so Manipal's rank contributed this much to CloudX Lab, this much to KBD. And Simplilearn's 0.15, how much did it contribute to CloudX Lab? Whole of it, right? Okay. Now what will be the end contribution of what will be the new rank of KBD? 0.15, that's a fixed number, plus how much is the contribution received? 0.075, right? That's the contribution received. So this is the new rank, and that comes out to be quickly 7 plus 5 is 2, 2, and 5. Good? So that's KBD's new rank. No, I'm sorry. I messed up. So it should be 0.15 plus 0.85, that's the formula, into contributions received is 0.075. Okay, which is, yes. Good? That's the new rank. Is everybody okay, or is too much of maths? Although it's a simple plain, plus minus. All right. Am I confusing you? Okay, great. All right. Now, here, the CloudX Lab, you see, is receiving how much contribution? This plus this, right? So the new value will be standard formula 0.15 plus 0.85 into the contributions, which is 0.15 was contribution from Simplilearn, 0.075 was contribution from Manipal. Okay, so you can see that the value is approximately this. Okay, makes sense to you? All right. Who can help me with Spark's now new um, page rank? 0.15 plus 0.85 into what will be the contribution? The whole of the rank, because it's giving vote to only person. So this whole value is going to one person, right? And this will be, so contribution is basically divided, and therefore divided by total number of people it's voting towards. Okay, now does it make sense to you? Ouch, thank you, Manu. I think you are right. You are right. I missed that part. So yes, KBD's new rank will also contribute to the CloudX Labs page rank. Okay. And the overall value is going to be, I'm using a scalar for doing this computation. Okay, it's like an insult of scalar with, I'm using it like a calculator. Okay, good. So now we have, yes. Good. Does it make sense to you? All right, very good question. So Nitesh's question is, what are the changes that will occur when KBD is also linking to Spark? So this rank will get divided by 2. 0.21 divided by 2 goes to CloudX Lab. 0.21 divided by 2 goes to Spark. Half of this value goes to Spark. Half of this value goes to CloudX Lab. Okay? So it's like who is more important in this network, and that's what we are trying to compute. Okay, is it clear? So Nitesh, we will not be really considering the contribution again, because we'll be making it half goes to CloudX Lab, half goes to Spark, and then what is the final value of CloudX Lab? It goes back to Spark. So in a way, this influence will be there, as well as this influence, direct influence, will be there. Okay, so this is the complex algorithm which made the Google one of the most successful companies in the world. All right. Now, what we did just now is we updated the value in real time. We did not use 1.0. Ideally, in the way Google guys did was Spark's value, CloudX Labs value, everybody's value was computed assuming their values to be 1.0, initial one. Instead of taking the latest value, they computed the values of each based on the initial value, the initial 1.0. Okay, and then once one round of updation was done, then the second round started, and they did it again and again. And this formula, they came up with this formula so that in the end, in after few iterations, like after 10-15 iterations, these ranks actually become constant. These ranks start converging. So this algorithm is actually iterative algorithm. That's why one is the computation of PageRank itself is iterative. Second is the websites keep on changing all the time, and therefore the crawling has to be done They crawl it into HBase, then run the PageRank algorithm in MapReduce, and they keep on doing it again and again to compute the PageRank. Okay, so this is what the algorithm looks like. All right, so we have tried to do the same thing here. So we loaded the links. Okay, we loaded the links and then gave all of the links an initial value of 1. Okay, we have said map values to 1.0, right? Remember map values? And then we are running this iteration 10 times. We are running this iteration 10 times. And then inside this, we are saying links.join ranks. Okay, these are the links. Yeah. So Sunny's question is why 10 times? It's just one number. The more number of iteration you have, the same graph, like here we can start computing these things again, right? Computing these things again as in when we are updating these numbers. All right, here we have done the real-time update. We could have done their calculation of individual, assuming others to be at 1.0, and then in the second iteration, we could have come up with a newer number, and then and so on and so forth. So the algorithm basically assumes links initially to be 1.0, does the entire computation of incoming and outgoing based on their initial values to be 1.0. It does not take, you can see the ranks is a separate, rank is a separate RDD. Okay, now you can see that links.join ranks, we are joining ranks and links at this point of time. These are initial links. Ranks contain the assumed value here. And then we are saying flat map. Okay, in this flat map, after joining, we'll get the links as well as the rank together. And then we are saying, what is the contribution? Okay, what is the contribution by dividing total number of links, outgoing links for each link. So here, this links contain the actual URL followed by actual key value is URL and neighbors, like this. All right, so that way. Now, once we are basically computing the same thing. First, we are computing how each link is giving how much contribution to somebody for each URL. And then once we find that out, that's the contribution we have find out, then we say that we does the rest of computation. Okay, the way we just did. All right, we do the computation like this. So here we are summing up all the incoming links. We are summing up all the incoming links. And then after we have summed up all the incoming links, we multiply that sum by 0.85 and then add by 0.15. Whatever we did manually, that's what here we are doing programmatically. Okay. All right. So that's about PageRank. So this is one example I'm trying to show you that we are using Scale as Spark for this. Also, please note very important part here that we have done persist here. Okay. Okay. So by the way, this code is in Python. I think the slide got jumbled up or something. I had written it in Scala as well. So we had two models for the same thing. Okay, so we are saying here persist. Okay, but why we are doing it persist? Because this links is going to be used again and again. Okay, this link is going to be used again, while the contributions are going to get updated again and again, but the links are going to be used in every iteration. That's why it's being used. So Manu's question is, what is lambda? Lambda is actually when you are defining anonymous function in Python, you mention lambda. Here in case of Scala, we generally say something like this instead of lambda. Okay, in case of scalar. All right. So this is how you can actually write a page rank, a, a very complex looking algorithm in Spark and get it done using uh, uh, on many machines. Okay, because links, if you're crawling, the links are going to be really, really huge, thousands, millions and millions of references, and therefore it becomes very complex very quickly. Okay, on the same lines, you can actually crawl Twitter and then build a kind of a relationship between you and all your friends, and then figure out who is more important amongst your followers or the people who you are following. Okay, based on the graph. So this is called graph computation, and here we are not using any standard algorithm for graph computation. We have built our own here. Okay, so this was our key value RDD with an example of PageRank. Okay. We also talked about persisting and partitioning. All right. So the next point, next slide is going to be pretty simple. Okay. So how to load and save data. Okay. So far we have either converted an in-memory data or you used HDFS file. HDFS file, we have so far dealt with only plain text file in case of big.txt. And in case of in-memory data, we have parallelized arrays mostly. We have not parallelized any kind of objects. Interesting part is the Spark supports wide varieties of dataset. Okay, you can access data through input format or output format. Those are the same interfaces used by Hadoop. You remember, we converted the input data block into input format, right? So Spark basically reuses the same libraries for reading data from Hadoop so that it can take the advantage of data locality. So every partition is generally made out of one input format. One partition is generally based on based on based on uh, so one input is split. One input is split generally get divided into multiple partitions on the same machine based on how many processors do you have. Okay, so that the data of a HDFS block does not need to be transferred. Okay, so also Spark, the same formats which are available for okay, so it can access the data using input format, output formats, which are available for many common file formats such as S3, HDFS, Cassandra, HBase. All those formats it does support. Okay, so there are few things to note about a file. There is a format in which the data is saved or data is represented in the file. It could be text, JSON, it could be sequence file, it could be protocol buffers. We can also configure compression. Okay, we can also configure compression if your data is compressed in HDFS or at the target location. Spark, while reading, can uncompress it. Okay, and various file systems. So in the URL, if you say hdfs:// or you say ftp://, it will read the data from FTP or HDFS. Okay, based on the protocol. Just the way your browser, you could either say http://google.com or https://google.com, or you could even say ftp:// something and so on. So that's protocol. In the similar way, Spark provides reading from local. If you say the name of the file is starting with file://, the same node on which the core logic is going to run, it's going to access the data from there. You could even say nfs://. You could say SMBs, Samba server, and so on. From S3, you can read just by changing the URL. Okay, so you can read data from structured sources, including JSON and Hive. We'll cover later. And databases and key value stores. So you can read data from all kinds of third-party databases. All right, JDBC database, Cassandra, HBase, Elasticsearch, and so on. Okay, these are the common file formats. So text file is standard. We have been using text file probably the oldest format. Then JSON is something we have already talked about. JavaScript object notation. CSV is the lines are separated by new line, and each line contains the values which are comma separated. CSV, yeah. Sequence file is a common Hadoop file format. Okay, in which it's basically binary key value. Key is the name of file, and the value is the content of the file. A sequence file is more like a folder compressed into a file. Like the way if you have a folder, you right click and say, create a zip file, right? So it's in the similar way, sequence file is a bundle of many files. While the name of the file is the key, value is the actual data of the file. Protocol buffers are similar to say CSV file or JSON file. It's a plain text format to represent complex data in a very simple manner. Okay, it's very fast. It's by Google, and it's being used at many places where the data is relatively structured, not like complex in case of JSON. All right. Then there are object files. When you want to save your own objects, you can use the object file. But object files are little dangerous. If your class, which has been saved as object in the file system, if the class gets more variables, then you cannot load the older data. So object files are relatively dangerous. All right. Good. So this is how we have been loading the data, right? This is how we have been loading the data. And yeah. Okay, this is something which we know. Now, sometimes there are many small files in a folder, like thousands of small files in the folder, and you don't want to process them. You don't want to process them one by one, one at a time. You want to process multiple of those at a time, right? Or in another words, let us say you want to compute the hash code of many files, right? Hash code as in MD5 hash or SHA-1 or any other signature way. You want to compute that. Or sometimes you need the whole file to be processed. In those cases, you can load the entire directory, and every record in the RDD is a key value pair. Every record is a key value pair in case of directory, and like this. Okay, the key is the URL of the file. Okay, and the value is the size here because we did this computation. We said that load this whole folder, and then each value should be converted into its length. So we are left with the size of the file. And then we said length.collect, and that's what we get. Is it clear to everyone? Okay. All right. Then we can actually save this like a normal text file in somewhere. Okay. So let's say there are a billion images that you need to resize, right? You can put all the images in a folder and read that folder as whole text file or whole files, right? Then you get the data in the binary format. Then you can use one of the Scala library or Java library to convert that data into smaller resolution, or you can resize that using standard library of Java and then save it and save as whole files back. So that way you remember our one of the only mapper kind of assignment that can be easily achieved. All right. So reading CSV or TSV is very straightforward. Read it as text file and then do the map and translate every line into array of values by splitting it or using one of the CSV readers. Okay, so you can see that we are reading CSV files using this jar. You can download this jar from somewhere, and while starting Spark Shell, we are saying dash dash jars and providing this library, which means this will get added added to the library of Spark Shell. But if you want to submit the job and you want to use Spark Submit instead of Spark Shell, in that case, you will have to update the dependency, the build.xml, with one or more dependency like this. Okay, it will automatically download it from there. Okay, now we are saying import this particular CSV parser, and then we are loading the data in a normal way where every record is a text line. And then for every record, we are calling CSV parser and then parsing the data. Okay, this will basically break down this into values. Further, here we could also say flat map instead of map. That way, every value will become a separate record. Okay, but that's not great thing because it'll merge the two records together if we do that. Okay, it'll merge this and this. Total number of records in the if you do flat map, total number of records will be 6 in the output. Here it'll be 2 records after map. Each record will be array of values. Okay, we could have just simply done here line dot split instead of using parser here. Okay, SBT is located in the current folder. Okay, in the build, there is the information is in the same folder where you run the SBT file, SBT package. Okay. All right. So does it make sense to you? Now, in the similar way, you can also load tab separated files. Okay, whereby you read the data as text files and then use either split by tab or you use a tab parser. Okay, you use a tab parser. Either way, you can use it. All right. Next is sequence file. It's a popular Hadoop format. It's composed of flat files with key value pairs. It has got markers. In this format, there's a marker. So there is a header in the sequence file which shows that which record starts where. Okay, that's marker. And it allows that those markers allow to jump between the nodes. All right. Remember there was a problem of record boundaries when we talked about input split and all. Those kind of problems are very well solved by sequence file. Okay. While creating input split of sequence file, it's very easy because it knows exactly where boundary starts. So we don't have to scan the data. Instead, we can just pick it from the header. Okay. So that's the advantage of sequence file. It allows Spark to read data in parallel from multi-nodes very easily, taking the advantage of data locality. So you can simply say sc.sequence file and you can load the data in sequence file format, or you can load the data from text file. After parsing or processing it, you can save the data as sequence file. Okay. So this way, it makes the life very, very easy and makes it very processable because sequence file is supported by many more engines, not only Spark. All right. Next is the so you can see that here we are trying to read the data and then saving at sequence file, and then we are reading as from sequence file. Okay, a question from Manu is how can we create a sequence file? Actually, there are many tools to create sequence files. The best way is if your processing is happening inside Hadoop or Spark, you can create using your MapReduce or Spark to create sequence file. Although what you can do is you can take any compressed file format, like zip file or tarp file or gz file, and then convert those into sequence file. There are many tools in open source available for the same. Okay, so there are object files which basically are simple wrappers around sequence file. Under the hood they are also saved as sequence file. Values are written out using Java serialization. These are intended to be used for Spark jobs communicating with each other. They can be sometimes very slow. Okay, if you want to use it, you can use save as object file, or for loading object file, you can use object file on Spark context sc.object file. Okay, so you can save any arbitrary object. That's here. This is one advantage of uh, using Scala, that you can utilize object files. Okay, so now please note that in these cases, this is good only if your data does not go beyond a job. Let's say today you ran a job, you saved certain data in object file format. Tomorrow, new code came in which the same class with which the same objects which you earlier saved, those have been updated. There are new functions, new methods, new annotations, or new fields in those objects. Now, when it tries to read the older objects and try to fit in older object files and tries to fit those object files into these new structures, it will fail. Okay, therefore be aware that object files are great if you don't want to reuse them in very future. It's great for keeping the temporary data. I mean, use sequence file instead, or the you use the plain text formats like JSON or other formats for storing complex data. Okay, I'm going to skip the Python way. All right, so there are many other providers of data store like HBase, many other providers of formats like HBase and MongoDB. They provide the input formats. You can use those formats for loading data from their place. Okay, so you can use Hadoop file, new Hadoop API file to read the data from the Hadoop supported URLs. Okay, by default, if you're running on the cluster, it assumes that you're trying to access Hadoop file. Okay, there's something called protocol buffers. It was developed at Google. It's pretty good for storing structured data and it's being used widely. Okay, so you define a kind of object, you define the whatever you are transferring or saving, you define it in a central format, and then it gets compiled to many other languages and can be used in many other languages. Same is case of thrift. Same is case with some more formats that have popped up recently. Okay, there are quite a few formats, and there are decent amount of formats available. We'll do the comparison later. Okay, to save the overhead of storage and network, we can use file compression. With most Hadoop output format, we can specify the compression codec and we can save the data. And this is generally done better. This is better done while configuring HDFS. So here it shows you a way to configure the compression in HDFS label itself. So we have already configured in our case. And therefore, while we say text file, even if the file is gzipped, it basically automatically reads it as text file. All right. You must have seen, you will see in future that if there is a ggif file, compressed file, and you try to say text file and read that zip file, it will automatically unzip it and access the data. Okay. There are many compression formats, out of which bzip2 seems to be more sensible to use. And these are there are, so the important part here that you should note down, or just remember, that when we talk about a format, a compression format, there are four basic criterias, or three basic criterias actually, three basic criterias to use to judge it. One, whether it is splittable, meaning if we have saved a file in that format in HDFS, and when we need to process the file, does can we process part of it, or do we need the entire file and then assemble that file and then do something about it, right? So the only splittable formats are LZO and BZIP. Okay. Next is speed, compression speed, compression or decompression speed. So out of which bzip2 and glib are slow, while snappy and LZO are fast. The third one is effectiveness of text. There are quite a few text files when we process, and and out of these, the compression which, you know, compresses text most effectively is bzip2. Okay, like the outcome will be really small file. Okay, a question from Kar. All right, that's good, Sunny. So we have configured most of these, and that's good that you have used Snappy. I'm happy, and feel free to share the work with others. Okay, maybe you publish it on your lab, on your GitHub, and then share with the team. Okay, a question from Kar. I have few questions. Spark is holding data in the memory, and we use this program to load data from files into Spark. Okay, so Spark is not holding data into the memory. Okay, Spark is Spark just takes advantage of the memory for during the processing time, but it doesn't really hold entire data into the memory. Okay. And next question is, we use these programs to load data from files into Spark. So we use this program to read data from files to process using Spark. Any other data sources are supported. So there are as I was telling you here, so there are quite a few data locations that are supported. Okay, there are quite a few locations that are supported. It can read data from almost every source. Almost every source. Where did it disappear? Okay, so it can read data from every source, whether relational database or MongoDB, HBase, HDFS, Hive, everywhere it can read. It provides all of those. Okay. A question is how we can retrieve data for analytics using a tool like Tableau. Okay, it's a good question. Okay, it's a good question. How would you use a tool like Tableau? So there is something called Spark also has come up with a small tiny tool, okay, which keeps on running in the background as a database engine called Beehive or Hiveline or something that I'm yet to explore. And using that, you can actually make calls to Spark SQL and then use that in your Tableau. Okay. Yeah, Spark kind of completely replaced MapReduce in many cases. Another question is when data from Spark is written to HDFS. So question is whenever you want to do, okay? When you say, when you have an RDD, you want to save it, persist it, only then the whole process actually starts. So you can say save as text file and so on. All right, that should be right. Did they make sense to you, Kar? Okay, so feel free to send me a one-on-one email so that I could answer your question, or if needed, we could have one-on-one session. If you have more doubts, I would love to do that. Okay. Question from Nitesh is what makes it faster? What makes Spark faster is that it utilizes memory, and it also utilizes a new way of doing the processing using the RDD way of doing things, so that the user is not tied down into only map and reduce. They can do many more things. Okay, when the user has flexibility of doing many more things, they can come up with many steps which can be compressed into a single step, making it far more faster than breaking down the job into map and reduces, saving the data into HDFS, then again reading the data from HDFS, processing it, saving it back, and so on. All right, that's what makes it faster. All right. So if you want to, the step to use protocol buffer is you can download and install protocol buffer compiler. And once you have installed the compiler, you create your protocol buffer file like this. Like here, we are trying to save our person. We're creating classes like person, phone number, address book. And once you're done with that, we can say protocol compiler. It will say, here we are saying Python out, which means it will create the class definition in Python code. We could similarly say Scala out, and we get the output in the Scala. And then we can use these classes in our Scala project and then use that. Okay. Use the protocol buffers to save it. So here we are providing source directory, this is destination directory, and so on. All right. So that way you can use protocol buffers for your project. If you have a lot of data, you want to persist it, and a lot of these objects, complex objects are there that you want to keep, then you define it in protocol buffers first. Then you run the protocol buffer compiler, which will generate the classes for Scala or Python, and then you load those objects, and then while saving, you say that save into protocol buffer using these classes, and then once that's done, it'll be saved in a files, and then you can use, while loading, you can again use protocol buffer objects to translate the raw data into the classes and then use it. Here is one project I have created for you. You can take a look at that. All right. So this project is where. All right. So you can take a look at this project. Okay. So here it has generated these classes for address book, person, and so on. Okay, that we can use. And while running, you can see that. All right. Now, okay. All right. If you want to handle Aljado, this is another question that people ask me quite often. One is enable Aljado compression in Hadoop by updating the configuration. In our case, we used Ambari to do the same thing. Okay. Then you create Aljado file by using this kind of format. First, we are saying that we are creating some data in bzip2. Okay. And so there is this file called bzip2, and we are saying that read this file, give it to standard output. Then aljado p is creating file.aljado. This is the file that's being created out of this compressed file. Okay. And once you're done with LZO format, LZO is again a format like zip, tar, and all, but LZO is more friendly towards Hadoop. Okay, I'll give you an exact use case. So let's say you want to keep the archive of the entire transaction of your web server, right? Of the logs, all the logs of your web server, and these web servers are in petabytes. These logs are in terabytes or petabytes. Now, you would like to keep the data in LZO format, right? Why? Because LZO is good with the text file, as well as LZO is splittable, meaning part of the if you get part of LZO, you can always process that file instead of needing entire data. How many of you have used zip file in the time of when a zip file get broken down into multiple files? I have used in the floppy days when we used to say that we want to split our file into multiple floppies, and then we would need all of these floppies one at a time to to combine the data, right? So why? Because we cannot really use zip or bzip or gz format or any other compression if it is split it into multi-parts. But in case of LZO, we can. Okay, we can unsplit, right? So here is one example that you can put LZO library in the class path, and then either if you're using the build.xml, then you can put this in the build this dependency in the build.xml, or you can put this dependency into SPT, as well as while using your configuration, while creating SC object, you will need conf object, and there you can say that my compression is this. Okay, you could also take a look at this particular URL. All right, so that was a quick look at the compression and the formats. So let's say you want to read the compressed file. You can simply say text file. It can actually read from this location. Okay, and please note that this kind of thing may not work great if you are running on Hadoop. Why? Because this will point to the local machine on which your driver is running, or your data is running. I mean your node manager. So since when you're doing the processing is going to run somewhere, right? So this one generally points to the machine on which the processing is happening. Okay, so a general idea is that if this file is available on all the nodes, then at the same location, then this does make sense. Okay, otherwise do not use this kind of format. It says that try to read the local file. Okay, so one way is you read the data like this from a local file, then you do the load it into RDD like this, and then you can start parallelizing this and so on. Okay, so if the data is not available on all the machines, read it locally on the driver node and then distribute using sc.parallelize. Okay, the popular option of S3 is very straightforward, and you can actually use this. I have written a blog post here which Abhinav has published here, and you can take a look at it. Okay, so you have AWS secret key and so on, ID and value, and you can read data from there. Okay, so you can read from HDFS. We have been reading HDFS for quite some time, and that's all. So S3, and so probably all kind of format, whether FTP, HTTPS, HTTP, Amazon, and all of that can be simply read from using Spark. All right. So, all right. Now, A common question is that how do we how do we carry the data to all the nodes? Okay, or how do we receive the progress from all of the nodes? We talked about RDD, but RDD is great if your data is really huge. And let's say there are small data, there's a small data that you want it to be available on all of the nodes, right? So when we pass functions such as map, every node gets a copy of the variable. Whenever pass functions to your map function, filter function, flat map function, every node gets a copy of that function, and along with the function, along with the things that go along with when you pass something to map, when we say my rdd dot map and we hand over the function, that point of time it notes down the function and all the variables being pointed to by the function, and it takes all of those to all of the machines. So all of the machines on which RDD has been mapped to gets a copy of those variables. If you change these variables, it's not going to impact, because if you change these variables while the processing is happening, it's not going to impact, because when the driver starts execution on all the nodes, a copy has already gone. Therefore, the nodes will not receive anything, and there's no way to communicate back changes. Therefore, keep in mind that it's not actually possible to keep on sending the continuous data to all the nodes. Even though there is broadcast variable, the broadcast also does not really happen instantaneously. So there is no way to immediately inform all the nodes about newer data, or immediately update nodes with newer data. Okay, so there are two ways of coordination between the nodes. One is accumulator, and other is broadcast variable. I'll try to explain. Okay, so let me first describe what is accumulator and why do we need it. The most important part is, why do we need such kind of thing? We remember that we have used so far an RDD, we were doing map, flat map, and so on. Okay, what if we want to receive, the progress continuously from all the nodes? As and when our lines text is being processed on every node while the process is going on, when you said, let's say sc.text file, this is my big.txt, and when we said xyz.save to hdfs, we want to see the progress, how many record have been processed so far and how many are left. In those cases, we can create accumulator object and hand over that accumulator object to all the nodes, and let all the nodes inform the accumulator that we are done with, we have done so many operations. Okay, so it can only allow, basically accumulators are one-way transmission. Accumulators are one-way transmission from every Spark application which is running on the node, from every Spark application node to the driver. Okay, and it's one way. Basically it tells whether to append things. Therefore, it's only great for associative operation, where the order of things do not matter to you. All right, where all the order of things do not. So how is it communicating over the network port? So every Spark application keeps on informing the driver via network communication. Okay, do it make sense? Okay, so accumulators are basically for one-way communication, such as you want to count how many records have been used. Honestly, other than that, I don't find much of a use case. We want to we want to continuously monitor what's going on. Okay, at every node. And that too progress. Or maybe for logs, we can use an accumulator. Let every node keep on logging the activity. Okay, so so it's actually pretty simple. All you have to do is call accumulator object. Let me just pick something. Okay, so it's pretty straightforward, as in you define an accumulator object. You define an accumulator object, and then while inside your map function or reduce function, you can inform the accumulator by adding something to it, or some other way. Okay, so that way you will always get an updated value. Okay, just keep in mind that you'll have to create an accumulator class, an accumulator object, and then keep on adding to it. Okay, all right, so you can create your own accumulator. That's out of question for now. Now, question from Manu. You mean to say that driver will keep one copy, and whenever change occurs, it will communicate an update? So driver, whenever there's a change that has been communicated from the node back to you, in that case, that accumulator will get updated. Okay. Yes. So whatever you said is actually correct. Okay. Yes. All right. The next form of communication is broadcast variable, right? So you remember our earlier discussion that when we wanted to, in case of MapReduce streaming, when we wanted to send our one file to every node, we used an option dash file, right? In the same way, there, what happened was when we said dash file, it actually took the script to all the nodes. Okay, it took the script to all the nodes, and that's all. Similarly, let's say in our cases, we want to take, say, small data to all the nodes, to take the copy of this small data to all the nodes that can be used on all the nodes. So that's where we use broadcast variable. It's more like, let's say there is list of words called stop words, right? And you, while counting the words in big.txt, you would like to avoid these words. So this list of words you will broadcast to all the nodes, and then use that. Okay, although you could define a variable like static variable and refer that variable from your map function or reduce function, but that's very inefficient way of transmitting data. Very inefficient way to transmitting data. That's where broadcast variables come into play. Okay, so for example, here we are broadcasting our common words to all the machines, and everywhere we're using dot value instead of directly using common words. We could have used common words directly as well here, but then it won't be using the broadcast way of dealing with things. Okay, so when we say common words dot value, we get this array. All right, sometimes we would like to use a legacy code in case of Spark. We can do that easily in case of Spark. Let's imagine that you have some R program. Let's say this is your R script. This is your R script, some R script. You can see we have made it executable by saying that env R script. R script is a program that runs any R script. Okay. So when we run this script, we get we get this output. Okay, this is running without Spark. Imagine that we need to do the same thing. This is similar to what Hadoop streaming did. This is kind of MapReduce streaming, making use of any existing programs inside your operations. In case of Spark, let's say you have this nice script, it's working fine, it's giving us great results, but you want to use this in a distributed fashion. Okay, so what you do is you say sc.add file and you put it here, and then you use the programs like pipe inputs and then pipe. Okay, this way it will basically call. Here we are, I'll tell you. So we are first defining these two variables. Okay, this is the name of the program, this is the location of the program, and we are saying that sc.add file. What does it mean? It means when we say sc.action, it's going to send this file to all of the nodes. Okay, then we define one function. Okay, one function, you can see we are saying these are the required fields, and we are saying return map lambda call f required. Okay, so here call f means we are calling the function. Okay, we are calling f here. See, call and square bracket f. Okay, now all right. So the important part here is that we are basically using the operating system's way of calling a program. Okay, only the role Spark is playing here is it's copying the script to all the nodes. Okay, it's copying this script to all the nodes, and here pipe inputs.pipe is a Python way of doing things. Yeah, this one is Python code. Sorry to not inform you upfront. So this is a Python code. All right. So all right, it's a similar one in case of scalar. So all I want to say is that yeah, SC is scalar, and this is PySpark, which is no here SC is Spark context. Okay, RS. SC means Spark context. So the mechanism, what I'm trying to say here is whether you use Java, Python, or Spark, Spark provides add file. Add file will make this file available in the current folder. Now, whether you want to execute it or you want to read it or you want to say you want to do whatever with this file, it's up to you. Here we are running it like a program. You remember system calls in C? Similarly, in case of Java, we can have a similar way, and Scala, we have a similar way. Okay. So you can call any program because whatever you write inside map or reduce could be anything, right? Flat map, filter, and so many of functions which we have discussed. Everywhere, it's up to you what you write inside the function. The function could be calling to making a call to database. The function could be making a call to say email server, might be sending emails, might be downloading websites, or your map function could be calling some other language and doing and compiling some other language. So it's up to you. What is it that you want to do inside your mapper and reducer, okay, or inside your transformations and actions? Okay. So it's up to you. What is it that you want to do inside the function? So sometimes you may want to call the R program. In that case, you can basically do sc.add file, and this script will be made available in the same folder in the local folder. Okay, so you can load this file and execute it then and there as part of flat map, filter, or any other thing. Okay, then there are numeric RDD operations like count, mean, sum, max, min, variance, and so on. You can use those For example, here we are trying to figure out the outliers. So it's pretty simple. We are just finding the mean and we are finding the, so I'll try to do it in scalar. So the difference is going to be array bracket. We could say var. Okay. So we have A, and you can see that there are, you could say summary. Okay, what is the function? Standard deviation. So it should generally give, yeah. So this much is our standard deviation out of these values. Okay, this is the standard deviation. These are statistical functions. If you want to find out, okay, let me just change. Okay, so that's that. I think that should do. Okay, so we are saying var mean, and then we are defining a function. Okay. Now what else is there? All right. Now let me convert the remaining part. Okay, so I'm going to answer your question in a minute. So here x is integer, or we could just say, all right, there was import math, right? I think import math. How did we import java.math? Yeah. So let me just check if does it work. No, I think we would need some other way. So we could actually do absolute x. Okay. Delta equals this, and then we could say if delta is less than 0, okay, define my function. It returns Boolean, and I'm returning this. So I'm saying if x is less than 0, x equals to x into minus 1. Sorry. Okay, so I'm saying where delta equals x minus mean, and whatever is the mean which we have defined earlier. Okay. If delta is less than 0, we are saying delta multiplied by 1 and then return. Okay. Let me see if it works. I'm not really, very proficient with Scala, but I'm okay. So what does it say? Return outside the method definition. This is okay if, okay, this is okay, I think, right? All right, let's say mean is 10 and is not outlier is how much? Say 1000. Oh, it's returning true in every case. So delta is this, and let's say x is 1000. Am I making a mistake here? Mean is 10, so we are saying delta is x minus mean. Now how much is delta now? Good. Looks like this is what? I see the standard deviation is actually far, far, far bigger. Okay, so maybe I'll have to be little more. So it has to be like x equals to 40,000. Okay, where x equals to 40,000, and then I think it should give. Okay, so yes, now this time it's okay. So the function is correct. It's just the value is little too high. Okay, so let me just keep it this way. So if we have, instead of a median, we have mean. If we have median, I think that should work fine. Or let's say mode. Oh, why? I think there was a way to. No, median is not there. We have only mean. Okay. So this way you can see that we can compute. All right. So now we can filter here based on this function. So if we are having, say, 5,000 record, one of the value is 5,000, we are running. Ouch. So these are not the outliers, while rest are outliers. Is it? No, there's something wrong. Are you agreeing with this logic? It says that these are not outliers, while rest are outliers. Again, oh, I said take 10. I get it. Now this is right. You can see. Actually, I did take 10 and then it gave. Okay, so here is the code in Scala. If you want to, let's say, find out who is not an outlier, okay? And if you just are looking for just finding out who is outlier, you could say here delta greater than or equal to this. In that case, you will find out who is an outlier. And so generally, a lot of data science is around who is an outlier. Okay. So here you can see that 50,000 is outlier out of these. Okay. How did we compute outlier? Is this clear to everyone? The way we computed is first we found a standard deviation. Standard deviation is a measure of what is the average way the values are moving are away from the mean or I think it's away from median, and then we computed the mean. Okay, and then once we have computed the mean, we basically computed the after that we computed all of the values, the delta away from mean, and then if they are you know more than 3 deltas away, if somebody is more than 3 standard deviation away from the mean, that means they are outliers. Okay, they are really outliers. Okay, does it make sense to you, or became too much of statistics? Yes. Okay, so it's fine with Hung and Srini. All right, so this way you can find out or remove the outliers as well. So the objective of this exercise was to tell you that there are something called accumulators and there is something called broadcast. Okay. Yes. Okay, so yes, the result is this. Okay. In the second case, so I'm answering Rahila's question. The earlier my result looked like this when I was looking for not outliers. Okay. And second time when we change the logic, when we change the logic to delta greater than this or equal to 3 times the standard deviation, that time I got 50,000. Okay. So out of our big array, these are not outliers. This is an outlier. Okay. Okay. Then we talked about that most of the statistic functions are already being ported to Spark. So we could always say on any of the data set, any of the RDD, we could always call these functions and we can get the results. So these are the statistics functions available to us. All right. So, all right. Now, okay. So we will continue about Spark runtime architecture and then quickly go through tuning. There's nothing much in these topics. And then we will talk about Spark streaming. I would love to spend more time on Spark streaming than both of these. Okay. So let's take a break for 10 minutes and back by 9:59 p.m. IST. All right, so I'm back. Should we start? Alvin, April, George, Jankun, Kar, Krishna, Manu, Mohit, Mohsin, Nitesh, Ravi, Shahida, Shamit, Hang, Pradeep, Rahila, Sunesh, Srini, Arash, Tegu, Srini, Sudhakar, Sunny, Treed, and Vikash. All right, so now we're going to start something really interesting. I'm going to skip these two topics for now. Okay, these are actually, we have already talked about most of these. We will come back to it again after some time. All right, it's not really too much required. And what I want to discuss is something really important. Yes. All right. Is my voice feebly audible to everyone? Should we start now? All right. So Spark streaming is a great extension to the core Spark API. It's a great extension to the core Spark API in the sense that under the hood, it's going to do the same thing like creating an RDD and do the job. Okay. So it basically processes the input data sets and create the output. All right. Let me just see. Okay. All right. All right. So yes. So what does it mean by stream processing? It is not same as what we did earlier. Hadoop streaming is not same as Spark streaming, please note. And this word streaming has been used, misused, and abused again and again in many cases. Okay, streaming, uh, YouTube video streaming, Netflix video streaming is totally different thing. Why streaming text editor SED or Hadoop streaming is entirely different thing, right? Here, it means a little different thing. Here, Spark streaming means there's a continuous input data coming in and we are processing that data. And if there is no data coming in, our processor would wait as long as there is no data. And then our processor will give out the result to somewhere as soon as the input data comes in. So the idea of Spark streaming is is okay. I'm just trying to figure out. I made some diagrams. Okay. All right. So let me try to explain. What does it mean by streaming first? And then we will talk about it. Okay. I'll give you an example, actually, a better example. I'll give you the example from my real life case scenario, and that's something that has changed my way of looking at stream processing. So let's take a case. In case of Amazon detail page, what you see here is this page, okay? Amazon.com, and I hope, say I'm looking for MacBook Air, okay? So the chances of getting a result from Amazon is very high, okay? So what you see here is this is the Amazon detail page, and this is the main image. It's called product image. This image is selected from thousands of images, and it is based on the feedback of every image publisher, along with the sizes, the pixel sizes, the resolution, the quality, and so on. Okay, so based on and there is a human intervention which basically marks these images. So for every images there are for every product there are thousands of images, out of which one image is selected. Okay, out of thousands of images only one image is selected. And now imagine there are few million products at Amazon.com. For every product, we would be doing recomputation as and when there is a change in any of these attributes. As soon as there is a change in any of these attributes, we get a notification of the change by the way of a queue. Okay, I'll try to represent it. So there is a huge queue at Amazon, okay, in which there are many people who are publishing the change. Okay, many people who are publishing that I have changed the title of XYZ product, okay, updated the image, and somebody has updated the, let's say, buy now, somebody has updated price, somebody has updated availability. Okay, so lots of people are updating the database of products, and instead of we listening directly to all of these, right, right. So instead of they telling us directly, what they do is they write to this message queue continuously. So there'll be all these updates will go as a message in case of organization wide. Okay, now it'll keep on it'll keep on getting updated into the queue. So all the people in the organization are basically writing to the queue. On the other hand, there are many people who are listening to it. Okay, listening to the changes, like some people might be sending email, the price has changed, send the discount, availability had changed, so send the mail to the warehouse people, and so on. So all of these people are basically continuously publishing their change into the queue, and these people on the other hand, or the applications or the bots, are continuously reading data from the queue. Okay, makes sense to you? All right, good. So this is a consumer producer kind of pattern. Earlier, what used to happen is let's say this is a consumer, okay, let's say, what do you say, email bot, okay, here image optimizer, image selector, and so on. Okay, so this is called at Amazon, this queue is called SQS. Okay, it's highly tolerant queue, similar to what we have Kafka in the open world. Okay, so these users are basically writing to the queue, and from the other side, people are reading it. Yeah. Now, earlier, before the queue pattern came into play, this one will basically inform to this guy, okay, directly. And there was tight coupling between the components, and API calls was happening all the time, and that was inefficient. So this SQS kind of queue came into play. Also note that Also note that in a lot of cases, people use databases for this, that in the central database, on one end, these will keep on informing into the central database, and from the other side, people are reading from the central database. That's also right, but here, what happens is a message expire after some time, okay? Message expire after some time and so on. Okay. Oh, yes, RS point is one time read only. Yes. So that depends on the way we configure our reader as well as we configure our queue. Okay. And also which queue are we using? So SQSQ makes sure that no reader reads the same message twice, as well as no reader should miss any message. All right. Make sense to you? Now, the important part in these cases is very important part, something very important. So such kind of scenarios, they basically you kind of all right. I think this is good. Okay, so these programs would continuously monitor the queue. They'll keep listening to the queue day in, day out. Okay, they will wait unless there is some data. As soon as there is some data, they will execute. So they don't operate on a free will. The way we say Spark Submit, it's we who are executing that program. But here, these programs basically are executed once and they run forever. Okay? They keep on running forever. So this is what I designed, this image selector, which would pick the changes from the queue and then do the selection. And that framework is being used by I designed a framework on which this image selector would run in a distributed fashion so that all the image selectors can run in the entire network and read from the queue and still have a good coordination amongst them. Okay, so this image selector is something which runs day in, day out. It doesn't stop. So one of the problems that you would face while designing such systems, which is very important to discuss, is how do you test? Okay, how do you test such program? The traditional way of testing has been run the program, check the output, and compare it with the expected output. But here, since this program is reading from the queue, it will run forever and it will not stop. If you try to kill it, chances are that some data is still lying in the queue and therefore you don't know that program has finished or not. Okay, so I designed a concept called poison, whereby you put the poison in the queue from this side, and whosoever is reading the queue, if they encounter poison, they shut down silently. Okay, they shut down silently because there could be thousands of such instances of image selector running on many machines parallelly, reading from the queue. Okay. All right. So this is called stream processing. Specifically, if these messages are millions of or say thousands of messages per second, then one image selector on one machine cannot handle those. So you might need multiple machines. Okay. This one running on some other machines here. Okay. And so on. So let's say here it is running. Okay, this is on some other machine, this is on some other machine, so that some messages are tackled by this, some messages are tackled by this, and they all parallelly operate without contradicting each other. Okay, that was another way of distributed programming, whereby our program would run in the entirety on all the machines. Okay, do I make sense? Did I give you a right example? Are you able to relate to it? So question from Manu, the incoming data will be in memory? No. Okay. Question from George, what if one selector goes down? Yes, exactly. And that's where my framework came into play, that in case one selector goes down, it bounces it back. Okay, good question. All right. Yeah. So question from George is, what is a poison? Poison is, because this program does never stop. If this queue is empty, it will stand and wait. As somebody said, consumer producer pattern, this is exactly the way it is. So it never stopped. The only way to stop these programs was that put the poison, put the poison here. Okay. How should I make a poison? Should I make it red? I think, yeah. So put the poison here. Let image selector consume the poison. And before dying, it puts the poison back so that other selector also dies. Okay, so all the selectors would shut down because of the poison. So that's poison. Okay, poison is specifically for shutting down the entire machinery. All right, there's a part of queue design. We call it queue design, and yeah. So you generally, whenever you're designing a program which runs continuously, you have to plan for testing out. And for testing out, we designed Poison. And that became quite useful in other circumstances as well. Okay. All right. So this is called stream processing. The data is coming continuously. We are processing it continuously. This is called stream processing, or the right word is unbounded data set processing. There is no boundary of data set. Data set is continuously coming in. Okay. This is also called as unbounded data processing. All right. So yes. Great. Now, the Spark streaming exactly comes here. Okay. Spark streaming is a library that runs in an infinite loop, reading continuously from the queue. Okay, and then creating an RDD out of it, and calling your logic on RDD. Okay, because because the logic inside image selector might get billions of record, and therefore logic of image selector might need to be run on millions of record. Therefore, what it does is, here it takes let's say these many records, then converts that into an RDD. It becomes it, becomes an RDD. So this becomes an RDD, okay? And then on that RDD, your logic would run as a mapper or reducer. Okay, this is what is going to happen. All right. Yes. Yeah. This is yes. RS. This is same as message queue. Any important right? Yes, that RDD will be distributed. That's correct, Manu. Question from RS. Any important difference between message queue versus Spark streaming? So Spark streaming processes data from message queues. This is one message queue, 0MQ. This is another message queue. This is another message queue, and this is another unbounded data source, the Flume, in which we are pumping continuously data from various sources. And Twitter, let's say we could write, there is a Twitter utils thing which comes with Spark libraries from which you can read data continuously to Spark streaming. Yes. So these are the sources of data. These are the places where data is continuously coming. Spark only takes care of processing it. Yes, it can be active MQ. Yes, right. So Spark streaming is going to be kind of message broker, as in it's going to process messages. Yes, Yes, George, that's how it will work. You remember, in case of Spark streaming, in case because it will run parallelly on all the machines. In case one Spark streaming, in case one machine goes down that were processing one of the partition, it will again somewhere it will come up. Okay. Yeah, you will get it very soon. You will get the idea. So these are the various kinds of queues from which Spark can read, or Spark streaming can read. Okay, so it reads data from these, and on each batch of data that it reads, like for 1 second or 1 minute or something, it creates RDD, and on that RDD, your programs will be run, whatever you have programmed. Okay, and then it can save data given out by your logic into HDFS, databases, dashboards, and etc. All right. So this is the workflow. Spark streaming is a library of Spark on top of existing whatever we have learned so far. It's just one extra for loop. Okay, it's an extra for loop which basically reads data from input stream, breaks it down into batches of data. Here, the data might be coming in milliseconds, right? It breaks it down into a bigger batches, like 1 second data, another second, and another. Okay, and then creates RDD for each of this batch, and on that RDD, it calls the Spark engine. Okay, so Spark streaming receives data from live input streams and divides the data into batches. Spark engine generates the final stream of results in batches. So the way you can imagine is, we call this D stream. Okay, D stream is a class part of Spark streaming, which is basically RDD created at the temporary time. Okay, so you will be programming against a D stream, not RDD. Earlier we were programming against RDD. D stream is kind of a wrapper. Okay, and every 1 second, whatever RDD gets created, all the functions what we have defined will get executed on that period of time. Okay, so data from time 0 to time 1, time 1 to time 2, time 2 to time 3, time 3 to time 4. That's what data is coming continuously. And then, okay, so this is the original D stream, which is coming. This is Windows operation. You can skip it. All right, let's try to do something more sensible. Okay, so all of you have to pay close attention to what I'm trying to do. Okay, so we are going to do word count for every 1 second. We are going to do word count for every 1 second. So first we change the log label to error. Okay, in the scalar. Okay, so we have changed it to only error. And then we import the streaming libraries. Okay, then we create a streaming context. This is the entry point to the streaming. Okay, on top of SC, we are creating SSC. Is everybody clear so far? Why we have done this error? So that this so much of info that comes in will become small. So I'll show you. So a dot collect, right? That was our RDD earlier, what we did before the break. You see, now there's no noise. Okay, you can also do that to reduce all of that logs. Okay, next is we are importing this. Okay, we are importing the library, a streaming library. Okay, then here we are saying create a Spark streaming context. Okay, for every 1 second of batch, whatever data comes in, SSC is going to create 1 second's batch from the input. Okay, and where is the data going to come from? We are saying SSC dot socket text stream, meaning open a socket at this local point. Okay, and then at this port. So we are saying where lines, and so it's going to listen to this port and read the data from there. Okay. Now, here the very important part is this is our kind of RDD looking thing, but it's not really. It's a wrapper on top of RDD. So whatever logic you write here would look like you are programming against RDD, but it's a D stream, and whatever logic you write will get executed every 1 second. Okay. So here we are saying words equals to line, flat map, is split by space. Then we are creating pairs, and then reducing by key. Basically, what we are trying to do is there is a lot of data data coming at this particular port. Okay, at this particular the service which is running at 999,999 is running that service, and we are trying to read from that service. Okay, and we are reading continuously. So this SSC, the Spark streaming, will talk to this machine at this port, and then it will, for every second, this logic will get executed. Remember this part. This logic will get executed every 1 second. Why? Because we have defined here 1 second. Okay, so let me, all right. Now we have then done print, but the process will not start yet. Okay, so those who have not got everything, I'm going to put it again to the window. Okay, this is first slide, this is second slide. Okay, is everybody with me so far? So in the first set, we are establishing the connectivity. In the second one, for every second, what has to be done, that's what we are saying. Lines is the lines gathered per second in an RDD. And then we are saying flat map is split that by space. Okay, and then convert that into pairs, and then those pairs we say reduce by key. So this logic, this piece of logic will get executed when we start it. But before that, we need to start one server. Okay, before that, we need to start one server listening on this port. Okay, -L makes it listen on this particular port. -K makes it choose some other port. Okay, let me open one more console. So you can also open one more console. Okay, so here we are saying SSH Sandeep Giri, and I'm logged in to the same host. I'm logged in. So the first one is the consumer. This one is the consumer. We're creating a service which can produce data continuously. And how do we do that? We start listening on this port. And whatever we type here, it's going to produce that data to the reader. Okay? It's going to produce the data to the reader. All right, so now we have created the service. Now move ahead and start processing it. Okay, not here. On the first one, we are starting this. Now wait for termination. Okay, so here you can see that it's continuously printing word count every second. Since there is nothing, it's printing nothing. Okay, now if I start typing here something, okay, you see it has done something. Okay, it has okay, let me just copy paste some data. I got better idea, so let me just copy paste this one. You see it has done the, okay, this is a cow which is hungry. Okay, so you can see that is has occurred twice. Okay, and has done the computing. All right, now I'm sure that doesn't satisfy your hunger for the experimentation. Now let me try something interesting. I've killed the service right now, so it started giving error because it's not able to read from it. I'm going to run a program called Echo. Okay, not Echo, Yes. How many of you have heard about this program called Yes? This Yes program is really, really, nice program. It keeps saying yes to everyone. And specifically, if you if you pipe this data through to your some installation program, it'll basically pipe y to it so that your installation can finish without you having to type y. So now you can imagine how lazy are the Linux programmers. Okay, so to type y so many times they have created a program. Now let's pipe this yes to NC. So this server NC 9999 is going to continuously produce y, which our process has to consume. Okay, it's already listening, looks like. Okay, let me go back. Ouch. Did I do something? I think somebody else has taken my port. I will start it soon. Okay, so again, since I've started the session again, I'm going to copy paste the entire thing. All right, let it finish. Okay, it's trying to connect to Metastore, no worries. Yeah, there's too much of traffic right now. What happened to this guy? All right, looks like it was a bad idea to give the port to somebody else. All right. Okay, so I'm going to do something. All right. Actually, the culprit in the whole game is this Hive server, because this one is connecting to Hive, therefore it's not really moving ahead. Okay, so this one is actually, okay, so looks like somebody is running Flume. Okay. E. So let me see if I can. Extremely sorry, I don't know whose process is that, but not able to. Actually, we have connected to the Spark, and that's what has caused a lot of issue here. Ouch. This has not happened with me yet. This is the first time it's happening. So if any of you is on Spark, can you exit? Yeah, maybe. I'm just trying to give the demo. Oh, that's not helping. So even after you have come out, Ravi and Sunny, I'm still stuck at the same place. So I'm still figuring out what exactly went wrong there. Yeah. No, I think there's some other issue. It's unnecessary trying to connect, actually. It's not. Otherwise, what we can do is we can run it like a script, do the Spark Summit, And yeah, actually, the biggest culprit out of all of this is the Hive server, and this one basically does not give me an option to skip. Let me just check one more thing. Am I able to run Spark Shell from another account? No, actually, no. All right, no luck yet. It's basically some here. There are some jobs running around, running there, and all I need to do is so there is a command called yarn using which you can do many operations with respect to Spark. Sorry, yarn. For example, you want to list all the applications running as part of yarn. So you can say yarn application list. Okay. So yes. So okay. Now it's running. I think Abhinav has stopped the service from my side. What he has done is okay. All right. So what you see is now using yarn application list, you can take a look at what applications are running. And also, if you have permission, if you are the admin, you can kill a particular application. Okay. And so on. Okay. All right, now it's running. Let's start the process again. Extremely sorry for the time we have lost. Okay, so let's start with first creating the connectivity. Okay, all right, let me just check. Yes, ouch. It's going to 8 port. All right, I'll just pause it for a minute. Otherwise, it'll overflow the network. Okay, so here we go, and we have created the connection. Then we are going to do word count per second. Okay, now is the time that we start the service. In case of Linux, you can always press Control Z to send something in background and bring it to foreground with FG. Now you will see that the moment we start the work, okay, the moment, although this await termination is not really required, okay, so what is it doing? It says 999 connection refuse. It's actually connecting to 999. Okay, now it should be okay. All right. Yes. Ouch. Why it's wrong? Am I running on same machines? All right, let me start from the beginning. So set the config. Ouch. Okay. All right. So is everybody with me till here? Then again, good. Then let's start the process on the second terminal. This one goes in the second terminal. So here we are going to produce some data, and then we are going to observe if it is being printed this side. So we're going to start the computation. You see, since we are not typing, this is my first sentence. Okay, yes, it is doing good. Now we are going to say yes to everything. Can you see this? This is the count, number of count Y is occurring every second. Do you see? It's around 500,000 on an average. You can see it's around 500,000 on an average. I hope somebody else is not consuming my data. Looks like this one which I'm skipping. I think somebody else has opened the port and also consuming the data parallelly. Okay, that's why I'm skipping these seconds. All right. So this way we can actually consume data at a very fast pace. And if we utilize multiple machines in Kafka, we can do billions of messages per second. Okay. All right. Since, yeah. Okay, so let it finish. Yes, it has finished now. There was some error, but it would recover from the errors and then start again. All right. So the program that was network socket that suffered from these memory issues, but In reality, in case of Kafka and other queues, the memory issues do not crop up. Okay, so did it make sense to you? Question from Hung, do you determine how many machines that consume data stream? No, we let this guy decide how many machines do we need. At most, what we can do is at this point of time, while we are defining streaming context, we can actually pass number of partitions here. Okay, number of partitions here, and that should do the job. Yes, that's the next thing, Kar. I'm coming to that. Okay. Yes, we can use the same concept for analyzing tweets. It is practical, yes. And as a matter of fact, RS, Spark has its own producer in case of tweets. Spark Streaming has a library for just continuously pulling tweets from Twitter. Okay, there is a library in Spark Streaming package itself. Okay, one of the person who was doing the project recently, he did that. He did what he did was he took the content from, he used Spark Streaming to continuously pull the data from the okay. Vikas's question is, can we have an example of XML? I'll have to create this example. I'll just note it down in the to-do. Okay, we have an example in case of Spark SQL that we will talk about. A question from Mohit, how to decide an optimal batch size to specify? It is generally a hard requirement from business. Do you want to update your UI per second, per millisecond, or per minute? It's a requirement from the business specification side. Okay. All right. Good. Now let's move on. So we had two parts. One is producer and other is a consumer. Spark Streaming was the consumer while NC was the producer. All right. You can do Maven and you can add all these libraries and use. Okay. Now moving ahead. Okay, question from Srini is, how do you see how much heap is being used? You can actually go up here. It says that successfully started service at a particular port. You see, not this one, 4040. Okay, so since my console is this much, so I can actually go to e dot, my console is on e dot cloudxlab. So there I can see here, okay, the jobs that are running since I had exited, so it's not showing much. Okay, generally you will get information about what you have cached, how much data is in memory, and so on here itself. Okay, the other way to check is, you know, using top or edge top. Okay, all right, good, good. Let's start with the rest. Question from Srini, Java, memory, heap space. Basically, you're producing just little too much and not consuming. Okay, because the yes command might be producing data at a very fast pace. Okay, so you can read data from either TCP connection, the one which we did just now. Okay, the one which we did just now, this part. You can read data from file streams like create a stream on a folder, and as and when new files are being added, it will pick up. You can create your custom actors by coding, and there are RDDs that you can use as a stream. Okay, so you can create text file stream given a data directory. Imagine that your Flume agent is creating more and more files in a folder. So you can actually create text file stream on that data directory. Every time a new file will get created in a folder, it will pick up that file and read that, and then you can process it. Okay, so you can make HDFS itself a queue. All right, and since Flume kind of programs are written in order to handle the continuous data, so Flume will write the data to HDFS, keep on creating files, and this text file stream will keep on reading new files and creating RDD out of it and executing your logic on it. So practically, almost everything is possible in the continuous processing models using Spark. Okay, I'm going to skip these parts, it's not required really. Okay, so Kafka is one such great queue. It's a publish subscribe messaging. Okay, and it's a distributed partition replicated commit log service. So question from Tegu. So we can manage and monitor application log using Spark Streaming? Yes, in case, let's say your application is generating a lot of logs and you want to process in real time, like you want to alert the L1 support system saying that such errors are occurring so frequently, why don't you just check, and so on, then you can build those kind of application using Spark Streaming. Okay, is that what you meant to do? All right. So now the Kafka is one such great queue which itself is distributed. Okay, meaning Kafka is not a single, one machine running on one machine. It's made up of multiple processes that handle the underlying load. It is distributed. It is partitioned, as in some of the messages are handled by one partition, some are another. It's replicated, meaning if one machine who is supporting Kafka goes down, you have somebody else to handle it. Okay, so so this exercise depends on these components. One, Zookeeper, other Kafka, because Kafka needs Zookeeper to discover its broker. Kafka is made up of Kafka brokers. Okay, and Kafka is made up of something called topics. So people speak on topics and others listen on topics. Okay, so Kafka discovers its brokers using Zookeeper, and this exercise it needs Spark and Spark streaming. Okay, all of the above are installed by default. Kafka library that you need is available in Maven, as well as it is available in this folder. Okay, similarly, we have created this project so that you don't have to worry about anything and can use it directly. I'll give you this project. So all right, so I'm going to go to second console and check it out. RM Spark EX. Okay, so now I have cloned my project. So here you can see that Spark Kafka streaming folder. Okay, so this is my Scala project. You can see here we are creating a conf object, creating SSC, as in the Spark streaming context. Here we are saying that consume message every 10 seconds. And then here we are saying we are creating the stream from Kafka. You see Kafka utils.create a stream, and we are importing these Kafka utils. In a similar way, you have Twitter utils, which you can basically use to talk to Twitter. Okay, and we are reading words, we are reading pairs, we're converting that into pairs, converting sentences into pairs. First one, this is standard code what we have written earlier, and then we are just printing it. Okay, and then we are starting and waiting for termination. All right. So this code should be okay to all. Here, the important part to understand is it's actually talking to Zookeeper. Remember, Zookeeper runs at 2181 port, and it's talking to Zookeeper and saying that from this group, can you give us, can you give us, um, can you give us a topic called say 5? Okay, it's I think the topic is yes. All right. I think here we are saying that get me a topic called map, and that's what it's using. Okay. So, all right. Now, so question from Sunny, why is it localhost? Shouldn't it be actual IP address? Since we are running Zookeeper service on the Zookeeper is running on the local host as well. So you can talk to any of the Zookeepers. It will internally redirect your request. If you are trying to modify, then it will redirect to the master. Otherwise, it can cater to you. Okay. If you have multiple zookeepers and you want to provide a redundancy, you can put semicolon here and provide other IP addresses. Okay, you can put semicolon, then you can say IP address, colon the port, and so on. Okay, that's the way you create a fault tolerant application. Question from Mohsin, why connect Zookeeper? So it's actually like this. Okay, so I'll try to say, so what do you get? Say brokers, broker 1, broker 2, and broker 3. Okay, and say this is, let's say, Kafka, or right. So it has many brokers, and they are all writing to each other and so on. So it's made up of, this whole thing is Kafka, and there is one more that I forgot the name. So yeah, so they discover each other using Zookeeper. Okay, using Zookeeper. So Zookeeper is running and we are talking to Zookeeper, okay, to discover. The Kafka itself will talk internally. Kafka is made up of brokers and clients. So all of these will discover each other from Zookeeper. Okay, since Zookeeper is also load balanced, that's why I was saying that instead of one Zookeeper, you could give a list of Zookeepers to it. Zookeeper, what do you call Zookeeper servers, and it will automatically start connecting. Okay, this code is clear to you. All right. Now, once we are done, we go to this folder. Okay, we go to this folder, and then we say Spark submit class jar along with the entire assembly. Okay, this is what we're going to do. It says it doesn't exist because we need to first do SBT package. Okay, SBT package. Okay, again, I'm going to git clone, and I'm going to give you all of this in a single shot. Ouch. Ignore those dashes in the beginning. Okay, so I've given you that. All right, good. Now this should work. All right, it's going to read data every 10 seconds, which I actually don't like. I'm exiting the scalar service here and going back to, okay, here is my code. All right, similarly, we can write code in Python. Now, so it seems to be running fine, and it's trying to read data from Kafka. Okay, it's trying to read data from Kafka every 10 seconds. I have a, okay. All right, now is the time that we talk to Kafka. Okay, you can log into that particular machine, and I'm trying to export path. Okay, I'm exporting path. Done. Then we're trying to create a topic called test. It says topic already exists, so we'll say test 15 Jan. All right, it should be 14 Jan, but never mind. Let's check if it's listing the topic or not. Okay, so where is the test 15 Jan? Yes. All right, so you can also take a look at this, and this would help you understand how to talk to Kafka. Okay, these are the commands that create your own topic. All right, now we can say that we can submit, I mean, we can create our own Kafka producer here. Okay, on a particular topic. You can find out this IP address by going to Zookeeper. Okay, we can find out this by going to Zookeeper and say this. Okay, so just as a check, Zookeeper client. You remember everybody tries to discover each other using Zookeeper. So this just to let you know that yes. Okay. All right. So there is one. I'm going to just pick up anything. Okay. Because any broker is okay for us. All right. So you can find out that the IP address of the Zookeeper is this one. Okay. So this is the IP address we are going to talk about. All right. 153 EC2 internal. So this is our broker. So for producer, we need to inform the broker IP address, exiting the Zookeeper because we have found one of the brokers. So we are talking on a topic. Okay. Now going back to our what process we started, because we changed something. We changed our code. We changed Kafka. I'm going to use VI. Okay, so here we are saying editing this file, changing the topic to, what was the topic? Yes, 15 Jan. We're changing our code to read 15 Jan. We could actually read it from the argument. Okay, and then we say SPT package. We say SPT package. So it's compiling now. There was one more thing I wanted to change. I wanted to change the time. It's just too much. The 5 seconds is little too high. 10 seconds is little too high. So I'm going to convert it into 1 second because it take too much time to. Good. So on one hand we have producer. This line is a producer. Okay. This line is a producer. And on the other hand we have the consumer. You can test whether it's producing anything by going here and saying test this and say read from the beginning. These are the utilities provided by this. Let me export this command. Okay, so just this is the utility provided by Kafka to see if it's working. See if it's working, right? Here on the second terminal, I'm running the consumer, second command. And the first one is the producer. From here, we are producing things. We have just produced SSS. And on the second command, it appears automatically. That means we are able to read and write successfully from Kafka. Now we have already created topic and everything. Now let's just produce something. Okay, we will just produce something and then consume it. All right. All right, so we go back to our submit command. Yes, Spark submit class, Kafka word count. These are the jars, and this is the jar that we have just created. Okay. Okay. So on one hand, we are going to write something, and on the other, we are going to. Okay, so this is nice, and let's see. Yes, so you can see here. You can see here. It's printing. This is nice here. I think I should stop. I think I should make one more modification here. I should say, what was that command? Yes. Okay, so this is the command. So I'm removing those logs. I'm trying to remove those logs. And since I made a change, so I'm compiling it again. Ouch, just a second. We can actually do. Let me just try if this works. This would work. What does it say? Conf.spark.conf. Oh, actually, we have to create a Spark context. So here we're creating conf label. I'll have to check what exactly, because here we are not creating the Spark context. We are directly creating a Spark streaming context. Never mind. So we'll just check later. For now, let's live with it. Okay. Or what we can do is we can actually, I got an idea. We can actually redirect. Question from Masin. What is it that JMS and message queues did not provide? The reason why Kafka was introduced is it was far more fault tolerant and distributed as compared to any other existing service. Okay, so I'm just redirecting its error or the uh, the error stream to dev null. Okay, and just trying to print something. Yeah. Okay. So you can see that we are able to do this. Next, I want to do is I want to run yes command and pipe it to Kafka. Now you can see. So we are able to go up to few 100,000 messages. We can further improve it by actually setting saying master equals Hadoop. Okay. In the Spark Summit, we could say driver as Hadoop. All right. So this is how. So on one end, on this side, we are producing yes, y, and the other end, we are consuming it. So the diagram is like this. Diagram is like this. Um, yes command is sending to, you know, Kafka, and from Kafka, Spark streaming is reading. Okay, and Spark streaming afterwards is creating these RDDs every second and executing your code on top of that RDD. Okay, so every second it's executing the code on RDD. Okay, does it make sense to you? All right. So it's the same thing what I have described to you. Okay, this is what we have done as an alternative. All right. So we have all kinds of operations on Spark streaming: map, flat map, filter, repartition, union, count, and all kinds of operations. Whatever we have for RDD on the D stream is the temporary RDD that's get created in future. For that, all of these wrapper things are provided to you. Now there is an important part. This important part which I struggled initially with. Okay, please pay attention. Just one more minute. So, while we were working with Dell, right, we were trying to fix their streaming problem. So we were basically doing exactly the Kafka way, and we were using Python for that. At that point of time, we realized that we are running the stream processing every second, but we wanted aggregate word count since morning as well. There, it was not word count, it was number of orders placed since morning. So we wanted to count that as well. In those cases, update state by key allows you to maintain a central hash table. Okay, so update state by key allows you to provide a key against which the you can keep on updating the value. Okay, you can keep on updating the value, and it basically helps you retain a central kind of a hash table. Okay, so we are basically giving that this is the existing value, this is the new value, what to do with it. So that's what is going to be our update function. This update function basically is being, so on our pairs RDD, every second update state by key will basically call the update function and update a particular key. Okay, so this will make sure that you can maintain a running count of something since morning till now and so on. This was quite useful when we had to maintain a count since morning instead of only for this small batch. Okay, so this basically helps you maintain statistics since morning. Okay, you have been provided with all kinds of operations. Okay, you can iterate over the records and others, as well as on top of batches you could create further window operation. Let's say you want to compute the statistics of 1 hour, last 1 hour, and so on. In those cases you could create window operations on top of Spark streaming. Okay, take a look at it. And on window operations are done on top of each batch, and therefore there are quite a few window operations. All right, and then we have join operations on window and so on. Okay, please take a look at it, and I would actually recommend you that you go through this blog. We have written a very detailed blog, and that one is actually more popular than uh, Spark's own blog. Okay, so we had streaming. This one, this is a quite a useful project. Those who are interested to do it, they should actually let me know. It's a very interesting project because it's the entire package. It's an entire package that we built, and it serves as a very good example for end-to-end dashboard. Okay. Yes. So there were few questions which I have missed. What is the different using only Spark streaming and Spark streaming with Kafka? So with the Spark streaming is general library to make use of Spark to process data per second, okay, or per minute per some window, okay. While Kafka is a queue, is a massive queue in organization. In an organization, you generally need a queue. On one end, people who want to inform others that, hey, we are done with this, we are done with this, they keep on pumping that information into the queue. Those who want to take a corrective measure or do something about an action, they listen to the queue. Okay, so it serves as a big notice board in an organization where everybody who wants to say something goes and write on the whiteboard, on a big notice board or a whiteboard, and then others who are listening to it, they read it. It's just that this big whiteboard has got topics on which people can write on it. Okay, do I make sense, Tegu? All right. Okay. All right. Thank you, everyone. We are planning to have one more 4-hour session. Either 2 plus 2 will be better for us. Okay, so we'll keep 2 plus 2 hour session, and I would love to take you through Spark SQL mainly, and then one example of MLlib and GraphX. Okay, and we'll also go through the 2 topics that we have left. Okay, so we are yet to figure out. I'll just drop an email to all of you. I sent a form. Please fill that form. Okay. So just 4 more hours, 2 plus 2, Kar. Okay. So how many of you have filled the form? Everybody? Okay, George. Please fill the form. It'll be great. I'll be able to take a call because I have to take a call by in couple of hours, and I would have actually loved to take one more weekend, but I have some other engagement next weekend, so I'm not able to. And if I don't take it next weekend, then it might delay further. So I want to take it now. And I sincerely apologize for making it during the weekdays. And if possible, I might figure out that we can do it on the next week. Yes, the course will be over this week itself. Yes, the last sessions look like they have been, little too much, but I think we need to maybe remove some of the topics from the course. The course is actually pretty big. In this course, we have actually covered the entire spectrum of the distributed computing along with the tools. Okay. Yes, I can have one-on-one sessions. That's not an issue as long as it's during the week. Okay, so first I like to finalize the class timing. Okay, and then then I'll send you the, okay. So all of you, please, you know, give me the, okay, please fill the form because that is easier for me to just take a call. Okay, so I have given you the form. Okay, all right. So I look forward for next session. I'm going to take you through Spark SQL, and we will try to do a couple of exercises like uh, preparing movie preparing movie data sets first, and then doing the using Spark SQL, we will try to convert unstructured to structured, and then we will do the movie lens movie recommendations using MLlib, and then we will try to do PageRank using GraphX. Okay, so I look forward to see you in these sessions and try to finalize the, okay. All right, looks like I have pasted that. Yes, I have pasted that here. Okay. So as soon as you finish, I'll let you know the project. As soon as you give me finish your project, I'll send you the certifications, the certificate. Okay. All right. Thank you, everyone. Thank you for being a great audience and asking good questions. I look forward to you in the next session. Okay. Bye bye. Have a great day.